you my mathematical brother, Professor Morten Nielsen. We don't look very much alike. And he will talk about shift invariant spaces and bounded mean oscillation.
Thank you, Matek. First of all, of course, I would like to thank the organizers for inviting me, give me this opportunity to give a talk here. And I guess I should declare that this is going to be a math talk. And I do claim to be a mathematician of some sort, at least. So, what I will try to convince you is that there are actually some interesting connections between the study of stability of systems in shift invariant spaces and the space BMO, that is the space of functions of bounded mean oscillation. So to speak, the road to get there is through like classical Fourier analysis, and I was thinking, well, that should be appropriate for this occasion, the Fourier talks. I should mention that what I'm talking about is going to be joint work with Hrvoje Sikic from University of Zagreb in Croatia. Okay, so let's look at the setup. Luckily, the setup is quite simple. So what I do is I take a single function, sin L2, and then basically, I mean, what I want to do is I want to create a function system from this function using very simple operations, and one of the most elementary, of course, is to shift this function around, translate it. So I can apply the translation operator on this fixed function, and then I get copies of this guy. And this is essentially going to be the type of system I'm going to look at. But I should also say that essentially what I'm interested in is stability questions. So one experience shows that one cannot pile these functions on top of each other too much. I mean, then you immediately run into trouble. So I want to have some spacing on the translations I'm going to consider. So typically what we do is we translate on a grid. Typically a regular grid, like here the integers, but it could also be an irregular grid. But I mean, there's no need to make the problem more complicated. So we are going to translate on a regular. And so what is the connection to Fourier analysis? Well, the connection is that, this is very elementary. I mean, if you take the Fourier transform of this translated guy, I mean, the Fourier transform transforms this into a modulation operator type the Fourier transform of the fixed function. So immediately we can kind of see that probably in the analysis of these type of systems, I mean, trigonometric series are going to pop up because, I mean, we have this elementary property here. All right. So to formalize the setting, I'm going to introduce what is called shift finite generated shift invariant spaces. So these are going to be subspaces of L2 of RD. And basically what I do, I allow for a finite number of generators of this space, and then basically I take these generators and then I translate them. As on the previous slide, then I take the span, how far can I get by linear combinations of these guys, and then I take the closure in L2. And this is going to be, obviously it's going to be a subspace, that's easy to check. And then the question is going to be, what are the properties of this space? And as you can imagine, I mean, that of course depends on the initial generators I'm going to put in. If I put in something horrible there, I mean, I cannot expect to get any nice properties out of this space. So actually, to get to the results that I want to talk about today, the connection to BMO, we don't really need this generality. So I'm going to simplify it to the very simplest possible case. First of all, I mean, whether we're on the real line or an RD doesn't really matter. So the first thing I'm going to do is, well, say we're going to be on the real line. It simplifies some of the notation. And on top of that, I'm going to say, well, you can definitely study, I mean, with several generators as above here, but let's just look at the simplest possible case where we have one generator. This is called the principal shift invariant space. And then, of course, the question is, why do we care about these type of spaces in the first place? Well, the reason, of course, is that they pop up in many important applications. And perhaps the most well-known, the most important, is that in the construction of orthonormal wavelets, through the multi-resolution structure, definition of the multi-resolution analysis is really given in terms of a persistent invariant space, a PSI space of this type, and this is the starting point of generating orthonormal wavelets. So just from that point of view, it's important. But also in many problems in approximation theory, spline approximation with radial basis function and the like, these type of spaces, they pop up, and we would like to understand what are the properties of these spaces. All right. So what I'm looking for in these spaces is what I would call a stable generating set. I want to have some way to nicely describe what are the elements in this space. Of course, I have the abstract definition, but I want to have another more concrete characterization. I want to be able to expand elements in this space in a good and stable way. And given that, the way the spaces are defined, the most natural thing is to look for stable systems that has exactly the same structure as was used to define the space. So we would typically look for a function phi that we take the integer translates of this guy, and then we don't ask for, we want to have this as the stable generating set. In many cases, what we simply do is to take the initial function, the one we use to define the space, to try to see can this function act as a stable generator for the space. But it may be that the initial function we used to define the space was ill-conditioned in some sense, and then it may be advantageous to shift, to change some other generator. But if you make a change of generator, what we want to require is that the space stays the same. And again, the prime example comes from the multi-resolution analysis, where we may have an initial generator that forms a Riesz basis. We're not happy about that because we want to do an orthonormal basis. So we make a change of generator of this PSI space to get a generator that forms an orthonormal basis. So this would be a typical example of where you change the generator. Actually, I'm going to come back to this point at the very end of the talk. So, basic Fourier analysis is really the tool. It's very elementary to do an analysis of these spaces, especially in the univariate case here. So, what we can just observe is that if we take an expansion in a system, a finite expansion of this type, and take the Fourier transform, then immediately what happens is that we get a trigonometric polynomial here with the same coefficient as here, and then the Fourier transform of the generator, or candidate. And immediately we can calculate the L2 norm of this guy squared, and so of course you have to integrate over the whole real axis, but you can chop that up into unit pieces and sum up, and put the sum inside the integral, and then immediately gets an integral of this type over the torus. The torus just being the integral from -1/2 to 1/2, say. So what we see here is that we are measuring the norm of this trigonometric polynomial that comes from up here, and then there's a weight factor here that pops in. But other than that, basically this is an L2 integral and L2 norm here. So what the calculation also shows is that if you look at this map, to take a trigonometric polynomial that is in this weighted L2 space, and we take the mapping onto this guy, we take the trigonometric polynomial multiplied by the Fourier transform of the generator, and then take the inverse Fourier transform. This is an isometry, and it's going to be onto this space. So this, very simple, this is very basic. Analysis shows that to study this shifted variable, this generating set here, candidate for generating set, what we really, or what is equivalent, is to study the standard trigonometric system, not in L2 of the torus, but in L2 of the torus with a certain weight. And this weight depends on the generator, or candidate here. So we have an exact expression for this weight. And now this setup, it's very easy to derive some of the basic results on this, these basis properties. because if you look at this set here, and you define the periodization function as before, like this, then it's very easy to check that in the case where this periodization function happens to be identically equal to 1, we immediately get an orthonormal basis for shift invariant space. I mean, this is really the optimal situation. We cannot do better than an orthonormal basis. Then we are very happy. I mean, the analysis is done, so to speak. Almost of equal qualities is the Riesz basis case, and there it's very easy to see that that happens exactly when this periodization function, this guy, is bounded from below and bounded away from 0 and bounded. If that's the case, you immediately get the Riesz basis property. What I should say here is, of course, this is now I switched to this univariate setting, but you can do equivalent, similar results in the finitely generated case. In that case, you have to look at the Gramian of the system and look at the spectrum of this guy, and look at the behavior of the Gramian. But basically, you can get equivalent type of results. Well, I should mention, I mean, Ron, among others, among the first to study these kind of results in the multivariate setup. And of course, Ron and Jen or other people involved. Okay, so this is basically, I mean, in the basis case, I mean, we have either the Riesz basis or the orthonormal basis. But now the question is, can we have some kind of stability even if this Riesz basis condition fails? Say that this periodization function is not bounded away from 0, for example. Can we still say something about stability of the system? And my claim is that we can, but of course we have to lower our expectations, so to speak. We cannot no longer have Riesz basis, of course, but we can have something not quite as good, but still stable. So let me just remind you of the notion of so-called Schauder basis, and as we mentioned here, I'm just giving the definition in a Hilbert space, so it's slightly less general than in the Banach space, but for this setting is sufficient. So I take a family of vectors that is numbered in some particular ordering, ordered in a Hilbert space, and then I say that this is a Schauder basis for this space if there exists a unique dual sequence of elements in the Hilbert space such that I can expand every element x in the Hilbert space in this way. So I take the partial sums from 1 to n and calculate the coefficients by these dual elements multiplied by xn, and then I want to recover x by initial elements in the norm topology. And what is important here is that I impose an ordering of the system, and these partial sum operators, they have to obey that ordering. So I'm not saying that this sum should converge regardless of the ordering. That's not the case for the Schauder basis. Here you have to really pay attention to the ordering. I mean, for example, wavelet systems in L2, LP, and so on, I mean, they are unconditional, so you don't have to mess around with the ordering. This is a good thing, because ordering the integers in d dimensions, I mean, it's kind of a mess, but anyway, for this setup, I mean, the ordering is going to be important. Okay, so from the basis results, I mean, we could see that probably by studying this periodization function P, we could read out some of the nice properties of stability of this generating set. So again, we have to study some properties of P, but now it's in a slightly different flavor. So what we have to use is another classical tool from harmonic analysis, the Muckenhoupt weights, and in fact you're only going to need them in the simplest case, the so-called A2 case on the torus. So what we say is that we have one periodic function, non-negative positive function from infinity. We say that this is an A2 weight if this condition is satisfied. So notice here that I take the average of the weights on an interval I, and then I compare it to the average of 1 over the weights on the same interval. And these two quantities, they have to balance out in such a way that the product here stays bounded independent of this interval I take on the torus here. If that is the case, I say that I have an A2 weight. I will give some examples in just a little bit. Okay, so with this definition, actually, 2008, someone I was able to prove the following result. So if you take your generator from L2, make sure that it's not a trivial case, and you look at the natural candidate for a stable generating set, then this forms a Schauder basis for this shift invariant space here. When you order the integers the natural way, you take 0, 1, minus 1, 2, minus 2, and so on. And this happens if and only if the periodization function satisfies the A2 condition. So you get a complete characterization of when do you have a Schauder basis for this shift invariant space. You simply have to check, what is easier said than done sometimes, that this condition is satisfied for the particular weight you have the candidate. I should mention that the result really is based on this well-known Muckenhoupt A2 theorem, where they start, in that paper they studied partial sum operators for the trigonometric system in weighted L2 spaces. And I should also mention that for a related system, the Gabor system, similar results they were obtained by Alex Powell and Chris Heil. I mean, this is kind of parallel cases. What I should also mention is that if you relax on having only one generator and allow the setting in full generality and as a FSI space, then generators in RD, you can indeed get an equivalent result, but it's much more tricky, and that would be a completely different talk. But what the basic tool is that you have to introduce A2 matrix weights, and then you have to define a so-called product class of these weights, and with that setup you can actually get equivalent characterizations, and then you get exactly, that you get a Schauder basis if and only if the Gramian is going to be in this A2 class, but I don't know, not rather than details. Okay, so just an example of something that is not at Riesz basis. So the first example is a little bit special. I'm going to return to this. So if you take and define your function psi in L2 by taking the square root of ln of 2 plus 1 times the characteristic function of 0 to 1, then it's very easy to check that this periodization function associated with this guy is going to be this guy. So this is a very, very slowly increasing function at the origin, but yet it's clear that it's not bounded. And a direct calculation will show that this guy is in fact, in A2. In fact, any power of this function is going to be in A2. I will return to that point a little bit later. So, and this is clearly not bounded. So this system, this forms a Schauder basis for the corresponding shift invariant space. But since the periodization function is not bounded, this system cannot be unconditional. So it's a conditional Schauder basis for this space. You can get a more simple example simply by taking some polynomial power of alpha is between minus 1/2 to 1/2. So here you have an unbounded guy. Here, if you take alpha to be something positive, you will see that you have a weight that dips down to 0, and in that way spoils your unconditionality of the system. But still, if you choose your alpha right here, you get a conditional Schauder basis. And by the way, these examples, they give alternative proofs of, Babenko, he has results on, explicit examples of conditional Schauder basis. But here, this setup really makes it easy to generate a variety of these bases. Right? Okay. So, now what has BMO to do with all of this? So let me just remind you that the A2 class is in fact very closely related to this class functions of bounded mean oscillation in the following way. So what is a function of bounded mean oscillation? Well, again, we take one periodic beyond the torus again, one periodic function, and then again we look at the intervals on the torus, and then we say that the function is in BMO if, whenever we look at, we take the difference between f and the average of f on this interval, integrated, take the average here, and if this quantity is bounded independent of the interval, so I can take this primum here and get something finite, then we say that this function is in BMO. So, how is this connected to the A2 class? Well, it's a well-known fact that if I take an A2 weight and I take the log of this weight, then I end up in BMO. And in fact, there is a partial converse to this result, saying that, well, if I take a function in BMO, then I can find some positive alpha such that e to the alpha f, that is e to the f to the power alpha, is going to be in A2. And this is a consequence of the so-called John-Nienberg inequality that you can always do that. So we can basically, in some sense, go back and forth between the A2 class and BMO. And what is going to be important for us is basically a trivial fact, namely that if you look at BMO and look at L infinity, then this is going to be, I mean, a subspace of BMO, because, I mean, you can just take an L infinity function here and put it in and use brute force to see that, well, the BMO norm is at most twice the L infinity norm. So, this fact I'm going to use, because now you might ask, I mean, what has this, all this has to do with integral translates? Well, the thing is that if I look at this system, then I notice that this forms a V spaces if and only if the periodization function was bounded away from 0 and bounded. But what does that mean? That means that when I take the log of this A2 weight, I end up in BMO, but since it's bounded away from 0 and bounded, it's exactly going to be an L infinity function. So the nice basis has the property, if I take the log of the periodization functions, I end up exactly in L infinity. So that gave us the idea that, well, so whenever you have a Schauder basis and take the log of the periodization function, you end up in BMO. The nice bases are the ones where you end up in L infinity. So could it be that you can use the distance from L infinity to the log of this weight in BMO, the distance in BMO, to put some quantitative measure of the quality of the basis? So the idea would be that closer you are to L infinity, I mean the closer in some sense you should be to the good basis, the unconditioned basis. So what is known is that L infinity is not a closed subset of BMO. So in fact you can show that the functions in BMO with distance 0 is exactly going to be the ones where you f, where you take e to the mf, and you say in A2 for any value of the integer m. And this is a consequence of the Garnett-Jones distance formula. I will not have time to discuss that in detail. But just to give you an example of a function that is distance 0 from L infinity and not in L infinity, I return to this example here, this ln of ln, of this quantity. This is clearly not bounded, and you can show by a direct computation that all the powers of this inner part here is going to be in A2. So this is exactly an example of a function distance 0 to L infinity. And now, so what can we prove of like improvements over the generic case? Well, so let's take a generator with a periodization function in A2, and then we look at the coefficient space for the Schauder basis. That is all the coefficient sequences generated by this dual system. And then we define this quantity epsilon as infimo of lambda is greater than 0, so that the periodization function to the power 1 over lambda is going to have finite A2 norm. Then we can in fact show that the coefficient space is going to be contained in the intersection of the LP spaces where P is between this P naught that's given by this quantity and infinity. So especially in the case where you have distance 0, you have the coefficients, the sequence space is going to be contained in the intersection of these LP spaces where P is between 2 and infinity. And this is in fact the best you can hope for in the conditional case, because you can, I did not state that, but you can prove that if you can go all the way down to 2 here, it's going to imply that your periodization function is going to be bounded, and then you immediately put back to the case that resembles the Riesz spaces case more. So for conditional basis, I mean, this is basically, it's an improvement of a general case, but you cannot hope really to get more precise information. So I guess this is a good place to stop. Thank you.
Any questions or comments?
What if I want a unconditional basis, not a Riesz basis, but unconditional? Can you eliminate when we'll get that?
Yes, I mean, this is very simple. I mean, as soon as in fact, you have a quasi-greedy basis, you don't even need unconditional. If you have a quasi-greedy basis of integer translates, it immediately means that the periodization function is going to be bounded away from 0 and bounded. So I mean, you do not have, I mean, you don't even have any quasi-greedy bases that are not unconditional. So immediately put back in the Riesz basis case. So they are the only ones.
Any other questions or comments?
In your definition of Schauder classes basis, is there a way to quantify it and to trace out how the H of Nord and what power it's parse out in constants?
Well, okay, okay. If I had more time, I would have actually shown you this slide, another result, that if you look at the partial sum operators for the Schauder basis and introduce the so-called basic constant, that is the soup of these operator norms, then you can, and you're in this case where the periodization function has distance 0 from L infinity and BMO, the log of the periodization function, then you can actually modify your generator by an L infinity function. So you get a new generator that has the property that the basis constant for this new system is better conditioned in the sense that the basis constant is essentially only going to be 3. So, of course, I mean, you could ask, well, can't I modify in such a way that I actually get to the Riesz basis or the orthonormal basis? But you cannot do that in the conditional case by an L infinity function because, I mean, immediately, I mean, this is a bounded and invertible operator on L2 you're applying here, so you cannot hope to map a conditional system onto an unconditional one. So this is the best, basically, you can hope for. So you can improve the conditioning of your system considerably. So your initial system may have horrible conditioning, but you can always change to another generator of this type to get a better conditioning.
Actually, I wanted to make a comment about, say, infinite-dimensional Hilbert spaces. There is an old theorem by Pełczyński and Zinger, probably more than 50 years old, that there are uncountably many mutually non-equivalent conditional bases.
Yes.
So that's kind of another part of the stick.
That's true. I mean, there's a wide variety of conditional bases.
Well, this let us thank our speaker again for it. Next talk starts 2:30.